This video is about the definition of work, the definition of kinetic energy. What is the work? How we define work? To define work, we need two elements. We need force and we need displacement. And we need two elements that are two vectors. So the first element is the force, is a vector force, and the second element is the displacement. And what we do with these two elements, we create a definition that say that the work is defined as the dot product of the force by the displacement. In one dimension, this means that the work that is a scalar quantity, because the dot product of two vectors is an scalar quantity, is an scalar quantity. Scalar quantity is a number. So the work in one dimension will be the force in the x direction by the displacement in the x direction. If you move in the y direction, the work will be the force in the y direction by the displacement in the y direction. If you move in two dimensions, the work will be the force in one dimension in the x direction plus the force, the components of the force in the y direction. So the essential point to understand here is that when you calculate the work, you calculate the force on the direction s by the displacement on the direction s. So if you have a displacement like this s, and the force is like this, F, you calculate the magnitude of the force in the S direction, this is the S direction, multiplied by delta S, delta S. So you calculate the work, and can happen two things, that the work can be positive or can be negative. If you take the direction S as positive direction, and the work is like this, and you move from this point to this point, the displacement is in this direction, delta S. So the components of the force is in this direction, Fs. So you multiply Fs by the displacement. In one dimension is always like this. It's the component of the force in the direction of the displacement by the displacement, and this is the work. And what are the units of work? Work are measured in joules. And what is 1 joule? 1 joule is the work done by a force of 1 Newton that makes a work during 1 meter. So 1 Newton per meter is 1 joule. So 1 joule is Newton per meter. 1 joule is 1 Newton by 1 meter. So this is the 1 joule. Okay, one possible example will be like this. Find the work done by a force. Let's say that the force is 3I. So it's a force that is pointing to the right. This is the force is 3I. And we want to make, this is the force F equals 3I. And we want to calculate the work done for a body, for an object to displace, the work done by the force to displace from x1 equal 3 meters to x2 equal 5 meters. So the first thing that we have to ask is, what is the displacement? The displacement is the vectors that go from x1 to x2. This is the vector displacement. This one is the vector displacement. How do we calculate the vector displacement? By delta x by I. What is delta x? Del is x2 minus x1 by I, so the displacement is 5 minus 3, x2, x final, minus x initial, I, so the displacement is 2I. So there are 2 meters between x equal 3 and x equal 5. There are 2 meters, right, is correct. So in the I direction, this is the displacement. So the force, the work is the force in the direction of the displacement. Oh, I have 3 meters in the direction, 3 newtons in the direction of the displacement. By the displacement is 2 meters, so the work is 6. But the formal way to do it is like this. The work is the scalar product of the force by the displacement, but the force is 3I, and the displacement is 2I. I scalar I is 1, so 3 by 2 is 6. 6. The other way to do it, because the work is F scalar dds, the dot product, is the magnitude of F by the magnitude of delta S by the cosine of the angle that form F with delta S. The other way to do it is in this way. The magnitude of F, 3. The magnitude of delta S, 2. The cosine of the angle, cosine of 0. So it will be again 6. What will be the calculations? You have to do it. What will be the calculation if the problem were that the force, that x1 equal 3 meters, x2 equal 5 meters, but now the force is minus 3I. The first question, first homework, is calculate the work. And the second question is, the second homework is what will be the work if you make the work to displace also from 3 to 5, but now the force is minus 3I plus 4J. What will be the work? You have to realize that the 4J is not making any work. So I leave it to you. 2 homework from the moment. I will remember 200 points I have to put. Okay. Well, this definition that we have used, the work equal the force by the displacement, the scalar product of the force by the displacement is valid when the force is a constant vector. Means a constant vector means that the vector doesn't change, does not change in magnitude, does not change in direction. So this equation F scalar dds, or magnitude of F by magnitude of dds by the cosine of alpha, is valid when F is constant. What happens if F is not constant? The definition of work when F is not constant is the following one. If F is not constant, we will calculate the work using something, because the work is an scalar, so we can sum scalar numbers. So we will calculate the work in small displacements. Let's go to see this picture. So the work is not constant, like this force. Let's say that is this force that is not constant. For every x, there is a different value of F. We will calculate the work on a small displacement delta x. So we calculate F of x, of this x by delta x. Fx of delta x, this is the small displacement here. So we calculate Fx1 by delta x, Fx2 by delta x. We divide the delta x final minus x initial, we divide it in n parts, and every part will call it a small delta x. So, for example, if x1 is equal 3, or 3, and x2 is equal 5, we divide the length that separated 2 points, that is 2 meters, in n parts, let's say 100 parts. So we take this delta x and we calculate the work by every force, considering that in the small delta x the force is constant. So we'll apply our equation Fx by delta x1 plus Fx by delta x2, etc. But we choose delta x1 and delta x2 and delta x3 the same one. So we can make the work like the sum of the force on xi by the same delta x, because we choose uniform delta x. We divide it in identical delta x. So this is the work. This is the work when the force is not constant. And what it means, this work? It means the area below the curve. The sum of fxi by delta xi is the area, the sum of all these small pieces, of all of these small stripes, fxi by delta x, fxi by delta x, fxi by delta x. At the end, if you sum with a delta x very big, that means that the end is very, very big, and we divide it in many, many parts to consider that in every part the force is constant. The work at the end is the area below the curve. So, what is the definition here? The definition is that first, in general, you have to take, as I said, the projection of the force on the displacement. And this is what it counts. What it counts to calculate the work is the projection of the force Fs by delta S, by this delta S. And now you sum the new Fs by the new delta S, and you sum. And like this, you go around the whole path. So you can consider also the work to be F parallel to the displacement by delta S. F parallel is the projection of is the force on the direction of S, is the force that is parallel to the displacement, where S parallel is the force parallel to the displacement delta S. Also, you can consider the force like F tangent. Of course, parallel to the displacement is the force that is tangent to the displacement. All these three definitions are. So with this, we ended here, and you have two problems here, two problems to solve. Okay, very, very equivalent definitions.